Hi, so now that we've watched those videos, now we're going to try some problems dealing with color values and RGB calculations. And so before we start that, I just want to ask you guys, were your art teachers just lying to you this whole time in your life? Didn't they always tell you that primary colors were red, yellow, and blue? Right? Weren't they red, yellow, and blue in art class? Where did this RGB come from? And so when I first learned about this, I felt very confused. And so really the difference is that there are primary colors of light and there are primary colors of pigment. And so the primary colors of pigment are what you learned about in art class. So for example, if I mix red and yellow, I'm going to get green. But if I mix red and green light, then I will get yellow light. So the light primary colors are more when you're talking about like the light spectrum. If you've taken a physics class, then you will have had some experience with this. And actually, your art teachers were kind of lying to you a little bit. And that's because the primary colors of pigment are not actually red, yellow, and blue. The primary colors of pigment are actually magenta, yellow, and cyan. And that's why if you open up a printer, you will see magenta ink, yellow ink, and cyan ink, because those three colors make the any color, any pigment that you need. And so they're kind of like the complements to the RGB primary colors of light. And so in our class, we're going to only be thinking about colors in terms of RGB values, because that's how computers see them. And so what color is 25500? And by the way the computer reads this isn't even just 25500. The computer is going to read this as 11111111, comma 00000000, comma 00000000, like that. But because we're humans and it's easier for us to use decimal values, we are going to read them as 25500. 255 is the highest value that you can get with 1 byte of data. And that's all ones, all on switches. And so this would just be red. And that's because it's all red, no yellow, or no green, and no blue. If I were to figure out what color 255, 255, 255 is, that would be no red, all green, and all blue. And so what do we think that would be? That would be cyan. Okay? And so the next question, since yellow is red and green, it is represented by 255, 255, Now the color can be made more greenish by reducing the red such that 200, 255. But the color can also be made dimmer by taking all those numbers and lowering them. So if I did something like 100, 127, 0, then that would be a darker, like darker green. And so, or darker greenish yellow. And so what value would represent a very, very dark blue? So what do you think? A very, very dark blue with a reddish tint. A very, very dark blue with a reddish tint. What do you think? Okay, so my estimate was 300 or 30, 0, 100. And so this is more blue than anything else, but it's still dark. So like if you're trying to make a dark color, then it would have to be like 100 or lower. And then a little tiny bit of red. Now your answer might be totally different, but as long as it's more blue than anything else, then you should be in good shape. And you can try to Google this answer and see how correct you were. And so the next thing I want to talk about is how to estimate the size of an image file. And so images are normally made up of either 3 bytes or 4 bytes. And so if it's a 3-byte image, then it has 1 byte for the red value, 1 byte for the green value and 1 byte for the blue value. Some images, like PNGs, have a 4th byte called the alpha channel, and we'll talk a little bit more about this when we get further into image processing. But basically the alpha channel tells you how transparent an image is, and so that's a 4th byte. But for now, let's just say that all images have 3 bytes to them, which, like, for example, JPEGs have 3 bytes to them. Now, of course, JPEGs are going to have other things, other meta information like author and date taken, and format and things like that, camera settings. But most of an image size is because of is due to its number of bytes and number of pixels. Okay, so if I have a 200 by 300 pixel image with 3 bytes per pixel, then that's going to be 200 by 300 by 3 bytes, which would get you 180,000 bytes, which is approximately 180 kilobytes. And so 1 kilobyte is 1024 bytes. The reason why it's 1024 bytes instead of just 1000, because like you've heard the prefix kilo, right? Like a kilogram is 1,000 grams. But computers don't like base 10. They're like, base 10, I don't know how to deal with that. Like I can't multiply by 1,000. So luckily 1024 is something that's close enough to 1,000, but it's base 2, so computers are happy with it. And everybody's just like, just multiply by 1,000 and you're pretty close. So I'm not that concerned about multiplying by 1,000 versus 1,024. Either way, 180,000 bytes is about 180 kilobytes. And so how would we figure out what size an image would be if it was 600 by 800 pixels? So 600 by 800 pixels would be a picture that is 600 pixels in length and 800 pixels in width, like what I have drawn here, which is not to scale. And so I want you guys to try and calculate what the size would be in bytes. So how many bytes would there be in a 600 by 800 image with 3 bytes per pixel? And so the answer here would be 600 times 800 times 3, which is 1,440,000 bytes. And so it's not going to be exact, but this is also going to be about 1.4 megabytes. Because there's about 1 million bytes in 1 megabyte. And so if I actually Googled this, it wouldn't be exact, and that's because binary is not base 10. And so I actually Googled it, and it's about 1.37, so still approximately 1.4 megabytes. So again, there's about 1 million bytes in a megabyte, but it's not exact. Alright, and then the last thing we're going to talk about is text. So text can also be displayed on a computer using a binary value for that. And so, for example, if I go to this website, these are ASCII values or Unicode values for each of the different letters. Notice that lowercase and uppercase have different values. And so that's because they show up as different on a computer. And so, for example, capital A is the number 65, or 0100000001. And so that. So can you tell me what the ASCII code is for the lowercase t? For lowercase t, what would the ASCII code for that be? Okay, and so the ASCII code for lowercase t would be 116, which is equivalent to 01110100 in binary, and that's how the computer would read it. Okay, so that's it. You're going to do a quick exit ticket on binary numbers, and then hopefully I will be back in school the next time I see you guys, and thank you for listening to all these videos. I wish I was there in person, but I hope you guys are doing well. Thanks, bye.